In this lecture, we are going to be discussing energy balances of increasing complexity and difficulty, and leading up to the rationale of why we would want to construct an enthalpy table to assist us in doing an energy balance. So we're going to call this one enthalpy tables. So for a simple, and I always like to put simple in quotation marks, energy balance, it would be of one where we have a single stream entering a process, a single stream leaving the process, and generally we are interested in solving for the energy. The energy balance for this system would be in equals out for a steady and continuous process, so we have no accumulation or buildup of energy inside of the system. We can write this entering the system. We have Q, which is drawn going into the process, plus the enthalpy entering in the form of mass coming into the system, and leaving the system, we have enthalpy leaving the system. We can write this also as the molar or mass flow rate times by the specific enthalpy of the inlet stream, and the molar or mass flow rate of the specific enthalpy leaving the stream. And since we are mostly interested in solving for the energy required to perform a particular chemical process, we can rewrite this expression by moving everything over to one side, say for Q. In this particular example, since there's no other mass flow rate streams entering or leaving the system, the same moles or mass that enter is the same as the number of moles or mass that leaves, assuming that there's no chemical reaction. And we can write the energy balance. Actually, apologize, I should have little dots over all these Q's here. We can write this in a compact form of the molar flow rate times by the change in specific enthalpy. And this is all well and good and a great approach for when we have a straightforward system of one stream entering and one stream leaving, because we can factor out the molar flow rate while then focusing our efforts on the change of the delta H of the specific enthalpy. Now, as we step it up in complexity, if we were to have a system now of still a single component, but now one stream being split into two, we'll label these stream 1, stream 2, and stream 3. We could potentially have a mass flow rate entering or molar flow rate entering, and thermodynamic properties of the inlet streams, and different properties of each individual stream. If we make this a case of water in the system, we have access to H hat as a function of temperature and pressure and phase in the steam tables. If we were to apply the energy balance to this particular system here, we again have in equals out. In this case, it's slightly more complex because we have a number of different streams. We'll have still an energy stream going into there in the form of heat. Entering the system, we have Q. Also entering, we have the flow rate of stream 1 times by its specific enthalpy. Leaving the system, we have the flow rate of stream 2 times by its specific enthalpy, and the flow rate of stream 3 times by its specific enthalpy. What we'd like to do is we want to rearrange this equation so that we have solving for Q, but in this case we have minus N1 H1 plus N2 H2 plus N3 H3. This is the energy balance for the process. And as we can see here, since we have N1, N2, and N3, there is no way that we can very easily define a delta H for the process that we could then calculate by substituting, perhaps C sub P delta T or whatnot. So what we instead need is we need a way that we can look up or determine what the actual values of these three specific enthalpies are. And since we are working with water in this particular example, we can go to the steam tables. If we don't have access to an experimental resource like the steam tables, we're then going to have to go through the process of actually calculating the H's ourselves, and that's what we'll talk about in just a moment. So since we have access to the steam tables, what we can do is we can look up H hat of 1, which is going to be at T1, P1, is equal to some value that we can just find in the steam tables. H hat 2 at T2, P2 is going to be equal to some value, and H hat 3, T3, P3 is equal to some value. Now, once we have access to these three pieces of information, coupled with the solved mass balance, we could then plug and chug the problem out and determine what our Q necessary for the process is. Now, the next difficult case, we will use an example of a flash separator as sort of a vessel to describe the necessity of constructing your own enthalpy table. So in a flash separator, we have our feed stream here, in which case it's going to have a particular flow rate of N dot A for the feed and N dot B for the feed. This would be for a two-component system of A and B, and it's going to be at some temperature of the feed and some pressure of the feed. The flash separator is going to be run at temperature and pressure, and that's going to be the case for the top stream, or we'll call the vapor stream, and the bottom stream, which is the liquid stream. So in a separate video, we have an example of how to solve a two-component flash calculation. So we're going to skip over the actual solution of the mass balance, and we're just going to assume that we have access to the solution. So we have a flow rate of A in the vapor stream, and we have a flow rate of B in the vapor stream. And likewise, we're going to have a flow rate of A in the liquid stream and a flow rate of B in the liquid stream. But what we need to know now is we have two different components, so two components, three streams. So our energy balance is going to have a total of 6 H hat unknowns. Just as with the previous example here, where we have one stream entering and two streams leaving, there's not a clear way to be able to define what is the delta H in the process. Now, since we're working with arbitrary components A and B, we are not necessarily going to have access to the thermodynamic measurements that we could just simply look it up. So ultimately what we're trying to create here is a table for component A and component B. And what we want to know is for the feed stream, for the liquid stream, and for the vapor stream, we want to know H hat A for the feed, H hat B for the feed, H hat A for the liquid, H hat B for the liquid, H hat A for the vapor, and H hat B for the vapor. Because if we were to write the energy balance out, so we'll write out the E balance. Again, this is in equals out because this is a continuous and steady process. Entering the system is going to be Q. We need to know how much energy is going to have to be put into the system to perform this flash separation. Entering the system, we have our flow rate of A in the feed times by its specific enthalpy, plus the flow rate of B in the feed times by its specific enthalpy. And leaving the system, we have the flow rate of A in the vapor times by its specific enthalpy plus the flow rate of B in the vapor times by its specific enthalpy. And finally, we have material leaving in the liquid stream. So again, if we have access to the material balance, that allows us to know each of the molar or mass flow rate terms in our energy balance, but what we don't have is the specific enthalpies. And since we're not necessarily working with a well-characterized compound like water, it falls on us to be able to create this table here that will allow us to have the values to simply just plug and chug the energy balance to solve for the unknown Q. For the flash separation, I generally like to define the reference state as the liquid stream, the liquid or bottoms stream. And I'll briefly comment as to why that's the case. What we're going to be doing is, once we assume our reference state, and this allows us to set this as equal to 0, so actually we're going to define this as our 0, we can set one reference per compound. And for simplicity, we are setting that the specific enthalpy for A in the liquid is equal to 0, and the specific enthalpy for B in the liquid is equal to 0. And the reason why I like to choose this as the reference point is because when we're trying to calculate the H hat for the feed and the vapor stream, we really only need to perform one calculation. Since the feed is generally a liquid, going from the feed to the liquid stream only involves effectively a C sub P dt calculation, how much energy it takes to change the temperature of a liquid. Going from the liquid to the vapor stream, we are at the same temperature. All we're doing is changing the phase. So if we have a means of estimating the heat of vaporization at the system temperature, it only involves one calculation going between the liquid and the vapor enthalpies. Hopefully the rationale behind that will be a little more clear once we work through the calculation. So the goal now is I'll focus on just one of the two components, but recognizing that the calculation is identical for the other one. What we're trying to do is we have now H hat of, let's just say, A in the liquid is defined as 0 as our reference state. Now what we want to do is find H hat of A in the feed. Same procedure would apply for H hat of B in the feed. And we also need to know H hat of B. Oh, excuse me. H hat of A in the vapor. And then the same approach would be for if we're starting with component B, we would just be calculating H hat B in the feed and the vapor stream. So in order to calculate these two terms, we have to determine changes in enthalpy going from this state to that state and this state to that state. So we'll start off going from the liquid stream to the feed stream. In this case, what we're interested in is calculating delta H from L to F. Now delta H, if you recall, is always equal to H hat final, the final state minus the H hat initial state. And for the case that we're working at here, we're going from L to F. This is going to be equal to H hat of F minus H hat of L. And since we're working with component A, this gives us H hat of AF minus H hat of AL. And the reason why I like to work this way is since we have defined H hat of the enthalpy, the specific enthalpy of A in the liquid stream, which is AL, is equal to 0, that means this term goes to 0. So when we're keeping track of the process that we're actually undertaking, we're going from a liquid at the conditions of the L stream to a liquid at the conditions of the feed stream, which is going to be equal to the integral from T to T feed of C sub P of the liquid dt. So what we're using here is we're using a delta H state change to determine the actual value of this table right here. So the number that we will be filling into our table, which is this unknown H hat AF, if we go back and take a look at it here, we are in the process of calculating this value right here. And again, the exact same process could be applied for the B stream as well. So what we're calculating is this particular value here, and what we would fill into our table is the same thing that we have in this delta H calculation, and it works out conveniently that way because we have the reference state canceling out to 0 over here. So what we would fill into the table is the temperature of the liquid and the vapor stream, which is in equilibrium at T. Compare that to the feed conditions of C sub P of the liquid dt, because that's again what we're working with. So if we go back to our diagram here, we are feeding the material at TF here, and the bottom stream is going to be in equilibrium with the vapor stream here at T and P being constant. So we can use the same approach for the B stream, so H hat of B in the feed, and I guess we should be a little more specific. This would be C sub P of A. The H hat of B for the flash separation would be T and TF, C sub P of liquid B dt. Now the next step would be to calculate going from the liquid stream to the vapor stream, and this is at T and P because they are in equilibrium with one another. So how we would do this is we would have delta H hat going from liquid to vapor, and we should all recognize that this is the heat of vaporization at the system temperature. Then we can write this as the final state minus the initial state, because that is the definition of the delta, and then we would fill in our actual values. In this case, we'll use A as the vapor, which is our final state, and H as the liquid, and again, this is our reference condition. So if we were filling in our table, H hat of A in the vapor stream would be equal to the delta H of vaporization at the particular system conditions of T. Now, one thing to keep in mind here, and then we would apply actually the same thing for B. I have to be a little more specific. This is the heat of vaporization for A, and this would be the heat of vaporization for B at the system temperature. So one thing to keep in mind, and we could fill these into our tables, and then the energy balance is simply a plug and chug. Now, the heat of vaporization is something that is a function of temperature, and typically we only have heat of vaporization at the normal boiling point. So in material property tables, we have delta H of vaporization, which is typically at what I'll call TB, which is the normal boiling point. And this is the boiling point at 1 atmosphere. And this is just out of simplicity. Back when someone in the lab was measuring these heats of vaporizations, they decided just to do it at 1 atmosphere because it was, the simple way to do it. And there is a video lecture available that discusses how we can estimate the heat of vaporization at some unknown or some arbitrary T and relate it back to the heat of vaporization at the boiling point. So that's saved for a different lecture. So going back to our table, we now have, we've defined our reference condition as the liquid flow rate stream. So the specific enthalpy of A in the liquid stream is equal to 0. The specific enthalpy of B in the liquid stream is not equal to, is defined as 0. Then we next talked about how we can calculate the specific enthalpy for the feed streams, and then also the specific enthalpies of the vapor streams. So I'll circle these in blue, performed here as the heats of vaporization. The final step in the process would be to apply our energy balance right here, and it would simply be a plug and chug situation, because now we know all of our mass and molar flow rates and all of our enthalpy terms, so we can then plug everything in and solve for Q. And that's the basics of how we would build an enthalpy table and apply it to a flash calculation.